Hello, this is our final project presentation from the Medlytics course. We are Team Unnatural Language Processing, which consists of me, Vivian, Jiwoo, Lucas, Ray, and Valentina.
So first, we would like to present our problem statement. Our problem that we decided to attempt to solve is that hospitals many times have a transcribed information about a patient, such as their age, their gender, and some of their symptoms. And our goal was to use these descriptions to classify each patient with a medical specialty, such as allergy or cardiologist. And our solution was to use a machine learning model and language processing to suggest such a medical specialty for each patient.
So here is some background information onto our project. So the first thing is natural language processing, which is also known as NLP. This is the field of programming that processes and analyzes large amounts of natural language data. So natural language data is data that is continuous, but is non-quantifiable, which means that it does not involve any numbers. That means it can be more difficult to process this because there is no computations involved. By being able to interpret human language, machines can help with many areas of online communication, anywhere from email, spam filters to translation software. Another thing that is part of our background knowledge is the recurrent neural network, or the RNN. This is a type of artificial neural network that can understand sequential data. Also, examples of this are like videos or sentences. Each iteration of information cycles through a loop, which means that each decision is based on inputs that are based on previous and post inputs. That means each input is based on previous inputs and those that come after.
Now we are gonna talk about how we develop the model. So before we creating our model, we first clean our data. So originally, our raw data has around 5,000 rows of patient transcript, which is a paragraph of text describing the patient condition or medical history. So we cannot use our model with this data directly. So we clean it through the tokenization. So we filter punctuation spaces and transform each unique words into a number identifier, turns a sentence into a sequence of number. After tokenization, we condense classes from 39 classes to 11 classes. So it reduced the noise and improved our accuracy. Also with stemming and lemmatization, such as like fainted to faint. And we also remove stop words like a the, and, or is.
The next most important part of our model would be the embedding layer. This would take in those sequences of tokenized data that we just generated and then returns a multi-dimensional vector for each word. I think we used around 64 in the original, in our final model. These vectors would be slowly trained over time to be grouped together into those with similar sentiments. This would allow the model to group together words that have similar meanings in order to process them in a similar way. And it would be able to use them in the following layers. So the next part is the long short-term memory layer. This is a slight modification on the regular idea of a recurrent neural network. While a regular one would mostly take into account those of the most recent words in the sequence. Long short-term memory layer is able to keep track of words far prior to the word it is encountering at that moment. This is done through a cell state, which stores information, carefully controlled by different gates, and it enables information to be stored in the long term. This allows it to put words in a proper context, even if the context is in the sequence-wise far beyond where the current word is. And then the final part, or perhaps the most important, is the transfer learning idea that you can use a pre-trained model with pre-trained weights in order to incorporate them into the model that we're using. And this would allow it to have a bit more context on a specific field. In this case, we're doing medical data. So we chose a BERT preprocessing and embedding model pre-trained on PubMed articles. This would have it be more familiar with the medical context and have it be able to classify words that are more obscure or pertain to more medical ideas. And this would be added on to the LSTM layers that we discussed and some more densely connected layers before returning the final result.
Okay, this is all great and really interesting, but right now we need to stop and ask ourselves, how is the model doing? So we did an assessment of our model with visualizations. On the left, you can see a confusion matrix with predicted labels on the vertical axis and true labels on the horizontal axis. For class number 3, you can see that there's a lot of red in both the vertical column and the horizontal row, which means that there are patients being labeled as class 3 when they actually aren't class 3, and labels that are class 3 that aren't being predicted as class 3. Basically, it's making a lot of incorrect classifications. Also, on the right, you can see the ROC, or the receiver operator curve. And for this curve, we want the graph to be as much in the upper left corner as possible. And most of our curves are. However, for that red curve that you see, which is the surgery curve, or class 3 again, there's a very big gap between the left side of our graph and that curve. And that was something that we wanted to change. So in order to change this, we wanted to do some model stacking, which is using different models and combining them to get a better classification instead of having a one-size-fits-all kind of solution. We wanted to use a binary classifier to determine whether this patient is in the surgery class or not, and then use a multi-class classifier to kind of classify all the other labels. This is because surgery was the class that was being misidentified the most, and also it took up about 30% of our data set. So we thought this might be helpful. Unfortunately, through rounds of testing, we found that this actually wasn't a very good way of trying to improve our model and didn't really come up with any results, as you can see with these two diagrams. On the left, again, we have a confusion matrix, this time with only 2 classes, and the diagonal from upper left to lower right is correctly classified, but that 52 were rows that were actually surgery, but the model didn't detect that they were surgery patients. So this isn't great. Also, on the right, for the ROC, for this classifier, you can see that for about half of the graph, the blue curve follows that diagonal orange line, which is the curve that would occur if our model decided classes entirely at random, which means our model didn't do very well for about half of that curve. So we decided to just stick with the multi-class model that we already had and try to improve that to get better results.
And finally, we have our results. Drum roll, please. So first of all, on the left, you can see our confusion matrix graph. The highlighted diagonal line across the middle is the part where our model correctly classified the medical specialties. And there's a pretty distinct diagonal line, so that shows that our model is relatively accurate. And so our testing accuracy is 54.8%, but while this seems low, high accuracies become increasingly difficult with multi-class classification, as we attempted to do. And so hence our classification was actually relatively successful, as you can tell by the ROC score and graph. And so our general ROC AUC score is 94.7%. And as you can see on the graph below on the right, all of the lines have pretty high accuracies and are covering the entire square and are pretty far from the diagonal orange line, which signifies if the classification was random. Thank you so much for listening. Any questions?